So there are different ways of ways of actually separating the pollutants and contaminants from the environment, or from water, or from soil, or from air, by using solvents, or by the adsorption process, by photocatalysts, by chemical reactions, by filtrations. So there are different ways to separate the pollutants or contaminants from your sample. By using sorbent means by absorbing the pollutants or contaminants using nanomaterial. By adsorption in the surface of a nanomaterial. You see, it is a nanomaterial. If this pollutant or contaminant is adsorbed in the surface of the nanomaterial, and it is then separated from the sample, or from the polluted sample. Here it is photocatalysis. That means this is a nanoparticle or supporting material, and this is the pollutant or contaminant that is adsorbed at the surface of the nanoparticle, and by means of photocatalysis, that means by the UV light, it the adsorbed pollutants are breaks down. Here it is UV light breaks down the adsorbed pollutant. So nanoparticle adsorbs the pollutants or contaminants. This UV light ad, uh, your, breaks down or dissociates the adsorbed material, and and the final products again dissolve. So by means of chemical reaction, what it is done, the pollutants or contaminants, either it is reduced or it is oxidized by nanoparticles, or it can be filtrated by a nanopore, a material which have a nanopore. So by all these ways, using nanoparticle, we can separate, or we can degrade the pollutant or contaminant from the environment. Now, what are the nanoparticles that are used for this purpose? So there are different classes of nanoparticles, but mostly use nanomaterials for the environmental remedies is inorganic nanomaterials. You see, these inorganic nanomaterials, they are mainly inorganic metal-based nanomaterials, and their application, if you see their application, they can disinfect, or they can separate the heavy metals, or they can reduce the chlorinated organic solvent. So you see, there are first silver nanoparticles or silver ions. They can disinfect a, a bacteria. This is a bacteria, Escherichia coli. They can disinfect a bacteria. Titanium oxide nanoparticles also water disinfect. It can disinfect water. Different types of bacteria, you see, they can disinfect these different types of bacteria. They can reduce or oxidize the aromatic hydrocarbons, biological nitrogen, phenanthrene, etc. This is metal doped titanium oxide. That means titanium oxide nanoparticle. Metal is doped on titanium oxide nanoparticle. They are also used to treat with water contaminant. There are titanate nanotubes, there are binary mix oxides, and these iron-based nanoparticles, these are most important. This is used actually nowadays. The iron-based nanoparticles, they are used to treat water for heavy metals, to separate heavy metals, and the chlorinated organic solvents. That means it is actually used in the effluent treatment plant, ETP. That means the wastage, the waste solution, or the wastage a of a industry. This is used to treat the wastage of industry so that the industrial effluent cannot harm our environment. So these are inorganic nanomaterials. We'll see it. We'll see slightly details. First, there is silver nanoparticles. Silver nanoparticles actually are well known for their significant antibacterial, antifungal, and antiviral activities. It is very useful. It is very useful for its antibacterial, antifungal, and antiviral activities. I had shown you how silver nanoparticles actually destroy a bacteria or destroy a virus. I had shown you when we studied the nanobiotechnology. Now, this silver nanoparticle. The action of silver nanoparticle is dependent on the size and shape. Actually, if the nanoparticle size is less than 10 nanometers, it is actually very much useful. If the size is silver nanoparticle is less than 10 nanometer, it is actually very much useful. If the size is greater than 10 nanometer, it is useful, but its activity decreases. And the shape, you will get spherical shaped nanoparticle. You will get a nano rod of silver. You can get a triangular shaped nanoparticle. It has been seen that the triangular shaped silver nanoparticle, it is very much useful for the bactericidal activity or fungicidal activity. That means if the shape of a silver nanoparticle is triangular, then it can act more than silver nanoparticle of your spherical shape or your the silver rod shape. So this is about silver nanoparticle. If you disperse silver nanoparticle to a water solution or to a contaminated water solution by different virus or bacteria, silver nanoparticle can destroy the virus, bacteria, or fungus from the contaminated water. From the contaminated water. It has been seen that the bacteria which is responsible for our cholera disease, Escherichia coli, it is completely destroyed by these silver nanoparticles. Now, the next type of inorganic nanomaterial that is used for water treatment, it is titanium oxide nanoparticle. It is actually It is actually used in the water treatment, and it is also used as water purification, sorry, air purification, and it is used as self cleaning surfaces or a photocatalytic application for water treatment. I told you what is photocatalytic application for water treatment. You see, say here you see, this is a nanoparticle or on supporting material. Say, for example, this is a supporting material above which titanium oxide nanoparticle is placed. Now, this titanium oxide, on this titanium oxide nanoparticles, the pollutants or contaminants, these are pollutants or contaminants, the pollutants and contaminants are absorbed by the titanium oxide nanoparticle. And this UV light from sunlight, or if you pass UV light on that pollutant, that is absorbed by the titanium oxide nanoparticle, then the the nanoparticle, sorry, the contaminant will be breakdown will be breakdown. So this is the photocatalytic activity. This is the, you see, photocatalytic application of water treatment. This is called photocatalytic application of water treatment. So So you can use why titanium oxide actually used it for photocatalytic application, because titanium oxide can be activated by UV light. Can be activated by UV light. It means the electrons from the valence band of titanium oxide nanomaterial goes to the conduction band by the application of UV light. So it can be used as used as a photocatalytic application for water treatment. Now, titanium oxide nanoparticle are used for air purification also. That means the contaminants or pollutants present in air is absorbed by the titanium oxide. It absorbed by the titanium oxide. So air purification, you can purify air also by titanium oxide nanoparticle. It is also used for water treatment. Now, you can use the titanium oxide nanoparticle as titanium, as nanofiber, or as nanorod, whatever it may be. You can use the different shape of titanium oxide nanoparticle for different purposes. So if you want to purify air by the titanium oxide nanoparticle, you can use a nanofiber. So Uh, there are other type of titanium oxide nanoparticle which is used to treat for the treatment of water and different bacteria. They are metal doped titanium oxide nanoparticles. Say for example, manganese doped titanium oxide nanoparticle. It is generally used for water to purify water from the 2-chlorophenol uh, 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 2-chlorophenol contaminant. So there are different types of metals of titanium oxide also. So there are different types of metal of titanium oxide nanoparticles also that are used as inorganic nanoparticles. The most important inorganic nanomaterial is uh, iron and iron oxide nanoparticle. It is actually a very much promising nanomaterial to remove heavy metals from water. Why? Because iron has magnetic properties. What is the advantage of magnetic properties? Say, for example, iron has absorbed something, absorbed a pollutant. Say, for example, if you have given some iron nanoparticle in the water solution, and this iron nanoparticle absorbed, say, some heavy metal or something it has absorbed in its body. Then you can easily remove the iron with that absorbed substance by means of a magnet. As because iron is magnetic, if you place a magnet inside or outside somewhere, then all the iron nanoparticles will accumulate on the magnet. And we can separate the iron nanoparticle from the solution. I have told you that the, the nanomaterial itself is a pollutant or contaminant. It is very dangerous. The nanomaterial is itself is a pollutant or contaminant. So we have to remove the nanomaterial from the solution. We cannot use any nanomaterial which can absorb or which can remove or which can react with the pollutant or contaminant. We have to separate that nanomaterial that is we have used from the solution. It is very important point. So either the nanomaterials will be biodegradable, or it can be it should be separated, or it should be regenerated. Something must have to do with that nanomaterial. The the beauty of iron nanomaterial is that you can easily separate that iron nanomaterial, or or the iron nanomaterial is not that much harmful for our body, because we have many iron molecules in our body. You know, we we take iron, and we require iron for to make our blood. That means we require iron for to prepare hemoglobin in our body. So iron is inside our body. So if iron enters inside our body, it will not do that much harm. So we use iron or and iron oxide nanoparticle as to as a remedial nanoparticle for the environment. Now, this iron nanoparticle, it has some disadvantages. What is the disadvantages? It can be aggregated. It can be aggregated. It can be aggregated means the nanomaterials are attached with each other. That is called aggregation of nanomaterial. Here it is one nanomaterial and it is another nanomaterials. Our intention is to separate this nanomaterial. But if it aggregates, if it attaches to each other, then it will not be a nanomaterial. Say if it attaches to each other, another nanomaterial attaches to each other, then it will be a macromolecule. So iron or iron oxide nanoparticles, they have a good tendency to be aggregation, tendency for aggregation. And after aggregation, that iron nanomaterials may be toxic after that aggregation. So it is a good problem for us to 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 your avoid this type of problem. To avoid this type of problem, uh, a core shell nanostructure. Can you remember the core shell nanoparticle? There is some core, and outside the core there is a shell. I have told you that that a core shell nanostructure, say for example, there is a silica core, and outside there is a gold shell. We have studied in the nanobiotechnology the core shell nanostructure. This core shell nanomaterial, it is called ZVI. ZVI means zero valent iron. Zero valent iron core shell nanostructure. In this zero valent iron core shell nanostructure, the core is iron molecule with zero, Fe0, oxidation state 0. The core will be iron molecule with oxidation state 0, and the outer shell has iron molecule with oxidation state 2 or 3. Say for example, you see here, this is a core shell iron nanomaterial. You see here, this is Fe0, this is the core, this is Fe0, and this is the shell. Here iron, the oxidation state of iron is 2 or 3, Fe2 plus or 3 plus. Now, in this shell, the iron is oxidized like that, FeOOH. Now, this core shell nanostructure, it is not aggregated. It remains like it. Uh, if you bring another core shell nanostructure by the side of it, it will not attach with this type of with this core shell nanostructure or with this shell. So you see, this black portion is oxidized state of iron, and the motile portion is the zero valent iron. So it is called zero valent iron. Now, what you see, this oxidized state, this shell, you see the heavy metals present in the solution. It is absorbed in the shell. It is absorbed in the shell. Or, or you see the chlorinated water. The chlorinated water, when it comes here, the chlorinated comes here, the Fe0, the core structure, the Fe0 reduces this chlorinated compound to, you see, the hydrogen related compound. So you can absorb the metal ion, the heavy metal at the shell, or you can absorb it at the core also. You see, you can absorb it at the core also, and the core material, what it does, it it reduces the chlorinated your compounds that is very much harmful for our body. You know, chlorine is very much harmful for our body. Or what you can do, you can graft many functional groups. You see here, you can graft, you can place many functional groups here. You see, you can you can place carboxylic acid here, you can place amine here, you can place this all these things here. So what is the advantage? I told you yesterday that, say for example, you have grafted amine group here. Then this amine group can coordinate. It's say you know there is a lone pair of electron in the nitrogen at the nitrogen of amine group. This lone pair of electron will be coordinated to the, say for example, copper atom. Now, what will happen if this is copper atom? If this is the copper atom, then the copper atom will be attached with, with this amine group. If this is a copper atom, see if I can. If this is a copper atom, then the copper atom will be, say, the copper atom will be attached to this amine group. So if I use a magnet now, the magnet will attract this iron molecule and automatically it will attract the copper molecule. So we can separate the your separate your your heavy metal from the contaminated water by using this iron shell core structure. You can use the mixed shell core structure also. Say for example, with iron you can use palladium, you can use cobalt, but all these are in research state. All these are in research state. Only this thing we are using this thing for the treatment in the ETP, for the treatment of contaminated water, because the iron shell core structure is safe. So so how actually I want to show you how the iron nanoparticle actually used for remediation of groundwater contamination. You see, a nanoparticle water slurry injected to the contaminated groundwater. This is a pipe. By that pipe, you are entering the nanoparticle water slurry here, and the contaminant levels around the injection level is reduced in a day or two. Around this level, the contaminated molecules or the contaminated water will be cleaned by reducing the contaminants. How they reduce it? You see here, they can reduce iron 0 can reduce this chlorinated substance to the, you see, chlorine is going out and hydrogen is coming in. This is reduction. By this process, uh, 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 it is reduced. The nanoparticles do not change by soil acidity, temperature, or nutrient level. This iron nanoparticle or other nanoparticle will not change, do not change the acidity of soil. That means your soil morphology will not be changed by this nanoparticle. So groundwater can be purified by these iron nanoparticles. There are other type of nanomaterials, uh, which are silica nanomaterials. Silica nanomaterials, they are versatile. They are versatile means you can find it everywhere. You can use it everywhere, and they are porous also. They are used as adsorbent and catalyst. They are used as adsorbent of contaminant or pollutant molecules, or they can be used as catalysts. It has an advantage of large pore volume. What is the advantage of being porous? As because they are porous, the contaminants or pollutants can go inside to the pore, and they are trapped inside in the pore. So, it is the advantage of silicon nanomaterial. It has large pore volume. It has tunable pore size. Tunable pore size means you can vary the pore size. You can vary. If you want this much of pore size, you can do it. If you want a big pore size, you can do it. By the time of the preparation of silicon nanomaterial, they are facile surface modification. You can vary its surface modification. There was very much facile for the surface modification. You can graft many things to its surface. You see, amine modified aerogel, their applications are in gaseous carbon dioxide H2S. That means they can remove gaseous carbon dioxide or H2S from the environment. Amine modified aluminosilicates and porous silica, they can they can remove gaseous carbon dioxide, aldehydes, ketones from the environment. Carboxylic acid functionalized as mesoporous silica. What is that? You see? Oh yes, I can show you. You see, this is a mesoporous silica. You see, these are the pores. These are the pores of silica. So if carboxylic acid is grafted like that, say for example, here it is carboxylic acid. This is carboxylic acid. This is grafted to a nanoparticle. So in this silica, silica pore, you can graft carboxylic acid functional group. So that's why it is called carboxylic acid functional mesoporous silica. Amino functionalized mesoporous silica. That means you have added amino group as a functional group to silica. It is used in wastewater heavy metals. Thiofunctionalized. you can place SH group to the silica. So it is called thiofunctional silica. Here you see, here you see, it is a silica nanoparticle. Here it is a silica nanoparticles and functional groups grafted onto the walls of the pores. That means if these are the pores, if you uh, say for example, this is a pore, this is a pore, this is a pore. Say for example, this is a pore, and you can graft the functional group onto the walls of the pore, onto the walls of the pore. You can graft the functional group onto the walls of the pore. Now, now you see, this is silica, and you have grafted here, you have the functional groups. Now, here is these are the contaminated air. What is the contamination? These are the contamination. These are the contamination. These are the contamination. These are the contamination. So if contaminated air goes inside this type of silica material, silica nanomaterial, then the contaminated, you see, the contaminate the molecules or the atoms that contaminates the air, that it 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 settles here, and pure and clean water comes out. It is trapped into the pore. This is a pore. This is a pore. You see here, this is a pore. This is the pore. This is the pore, and the molecules, the contamination molecules rather, these are trapped into the pore, and clean air passed out from here. So this is the process of using silica nanomaterial. These are the grafting of your functional groups. There are many type of functional groups or many type of polymers. You can graft it here. You can graft here by different ways. You can graft it by in situ polymerization. You can graft it by physical impregnation. You can graft it by covalent tethering, that means covalent by covalent bonding. There are different ways by which you can graft the functional groups to the walls of the silicon pores. So these are the inorganic nanomaterials. We can use another type of nanomaterial that are carbon-based nanomaterials. What are the carbon-based nanomaterials? Generally, you see, you all know what are they. Fullerenes are carbon-based nanomaterials, single-walled carbon nanotubes, multi-walled carbon nanotubes, graphene. You all know about this. Fullerenes, you know what are 60 fullerenes, football-shaped your carbon nanomaterials. You know what is single-wall nanotubes, what is multi-wall nanotubes, what is graphenes, everything you know. So how it works, you see, these are, you see, this is a fullerene, this is a nanocomposite, or this is carbon nanotubes. So when light, UV light falls on this type of nanoparticles, electrons from valence shell goes to the conduction band. that induces the photooxidation of the contaminants. If you have organic contaminants in the system, then if you use carbon-based nanomaterials, then the organic contaminants adsorb to the carbon-based nanomaterials, and the ultraviolet light oxidizes, photooxidizes that organic contaminants, and you will get water and carbon dioxide. These are the how carbon-based nanomaterials works. There are different procedures for different types of carbon based nanomaterials. For example, fullerene works in one procedure, but carbon nanotubes works in another procedure. And the last one is polymer-based nanomaterials. It is not a very popular one, because polymers are aggregated. Aggregated means it do not remain as nanomaterial. It becomes a macromolecule. Only dendrimers. Do you know what? Can you remember what is dendrimer? Dendrimer means a large polymer with a definite tree-like shape. Only dendrimers can be used for to remove the contaminant. So you see, this is the dendrimer. This is a dendrimer, and the contaminant trapped inside the dendrimer. The contaminant trapped inside the dendrimer. So polymer-based nanomaterials, if you see the polymer-based nanomaterial, only dendrimers. I have shown you what is dendrimer, how it works. I told you how it works. Only dendrimers can be used. The heavy metals can be trapped inside the dendrimer, or it can be absorbed outside the dendrimers also, because here you see in the dendrimers there are NH2 groups or SS groups at the periphery of the dendrimer. So the NH2 group can donate a lone pair of electron to the heavy metals, and it can connect the heavy metal outside its periphery, or it can trap a heavy metal inside it. So it is a useful one, but dendrimers are very costly, very costly. So if you use this, it will be very costly costly remedy of water or environment. Remediation using magnetic nanoparticle. This is actually in the research level. Researchers from Rice University have shown nanoparticle of rust. You know what is rust? The iron rust. Nanoparticles of rust can be used to remove arsenic from water using a magnet. The actually arsenic sticks to the nanosite rust, and your magnet can separate that arsenic. That actually magnet separates the iron, and automatically arsenic is separated by the magnet. and remediation using aerogels and solid absorbents. You know what is aerogel? Aerogel is a type of gel or where some which have a large surface area and it has a very absorbing capacity. It has very much absorbing capacity. So if oil spills somewhere, if oil spills somewhere, this aerogel can absorb the oil and separate it from the environment. This is also is in the research level. And finally, nanomembranes and nanofilters. Nanomembranes and nanofilters means the filters means they have a pore. If if this pore is in nano range, then it is called nanomembrane or nanofilter. You can filter it by means of nanoporous substances. Some other nanoparticle, silver doped titanium dioxide, used to remove this. This can be used to remove this. These are the targeted, actually, specifically. This nanomaterials are specifically targets to the to a contaminant. That means silver doped titanium oxide nanoparticle can remove only 2,4,6 dichlorophenol from the environment. So if you have an industry which have a effluent 2,4,6 dichlorophenol, then you can use silver doped titanium oxide nanoparticle to remove 2,4,6 dichlorophenol. That is the target. You see, multi-walled carbon nanotube that can be used zinc ion. Carbon nanotubes can be used to remove fluoride ion. Gold coated with chitosan or chitosan polymer that is used to remove this zinc copper from the aqueous solution. Iron coated with carboxymethyl cellulose polymer matrix, it can be used to remove chromium hexavalent chromium from the aqueous solution. This dendrimer, PIMM dendrimer, can be used to separate carbon dioxide from free gas mixture of carbon dioxide and nitrogen on porous substrates. So these are very much targeted. That is not universal. You will not find any nanoparticle that universally separate all the contaminant or all the pollutants. And everything I have told you, everything of this are in research stage. Research stage. All these things are in research stage. Some portion of that, say for example, I told you the iron shell and core nanoparticle. It is used. It is used to separate some your heavy metals or chlorine-based pollutants or contaminants. But maximum of them is in research stage. So this is the end of this chapter.